Good evening. I'm Michelle Wirefiler, a student with the University of Washington's Engage program, and I'm here to welcome you tonight. My research is all about eavesdropping on the low, booming calls of fin whales, and on April 24th, I'll be here to talk about how those calls shake the earth and get picked up accidentally by earthquake sensors, so I hope to see you there. I get to have this opportunity because of the special collaboration between Town Hall and the University of Washington's Engage program. Together, they host the series called UW Science Now as part of the Seattle Science Lectures. Sponsors include Microsoft and KPLU. And now to our first guest. Megan Cartwright is a PhD student in toxicology at the University of Washington. Before coming to the UW, she worked for several years in academic research after earning her bachelor's in biochemistry from the Ohio State University. Outside of the lab, she likes to read and write science fiction, run and eat extra sharp cheddar cheese. Tonight, she's going to be giving a talk entitled Faster Laptops, Better Drugs, Worse Lungs: The Perils and Promises of Carbon Nanotubes. In her talk, she will be telling us about the ins and outs of these tiny man-made fibers. Nanotubes are fascinating and very versatile, but they may harm the lungs of the people who make them. Please give a warm welcome to Megan Cartwright.
All right. Thank you, everyone. Thank you for that lovely introduction. I'm delighted to be here tonight to talk to you about faster laptops, better drugs, worse lungs: the perils and promises of carbon nanotubes. So I'm going to start at the very beginning, which in our case is in 1991, when a Japanese chemist by the name of Dr. Sumio Iijima announced to the world that he had discovered how to make helical microtubules of graphitic carbon, or as they mercifully came to be known as, carbon nanotubes. And one of the best ways to envision what a carbon nanotube looks like is to picture a sheet of chicken wire that is then rolled into a hollow tube which is really long and really thin. So thin, in fact, that it would take about 10,000 carbon nanotubes to equal the width of one human hair. And in fact, when you look under a really powerful microscope, that is what carbon nanotubes resemble: little tangles of human hair. Now, why people were so excited about carbon nanotubes is that they actually have these really useful properties. For their size, their really tiny size, they're very lightweight, and they are incredibly strong, stronger than steel if you pull them along their length. So in the years following Dr. Sumio Iijima's announcement, researchers and engineers figured out that if they wove carbon nanotubes together or incorporated them into polymers and plastics, they could then use them to make really cool things that took advantage of their lightweight and their strength. For example, bikes that would go on to win the Tour de France, or $20,000 custom-made bullet and stabbing-proof suits. But that's not all from carbon nanotubes. They have really useful electrical properties too. Researchers at Stanford University have figured out how to make transistors, so electrical components in laptops, computers, out of carbon nanotubes, and are hoping to take advantage of these nanotube transistors to make even smaller ones that are more energy efficient in the future. And finally, most exciting, in my opinion, carbon nanotubes are being developed into awesome things in medicine and biology. Things like better ultrasounds and even cancer drugs. Now, how they use carbon nanotubes in cancer drugs, it's not like those sheets I showed you earlier. They actually take individual nanotubes and coat them in the cancer drug on the outside, almost like dipping a biscotti in chocolate, which can then be injected into the bloodstream, the nanotube, not the biscotti, and go around and go into the tumor where it delivers the cancer drug. So why are carbon nanotubes so versatile? Why do they have so many applications? And it comes down to basically, there's a lot of different varieties of carbon nanotubes. There are ones that are kind of longer, there are ones that are shorter, there are ones that are thinner and thicker, there are ones that are covered on the outside with chemicals, and then there are ones that are bald and pristine. So it's not surprising that given this variety of carbon nanotubes and this versatility of what you can make with them, that people were extremely excited in the years after Dr. Sunojima's announcement, and they began to make lots and lots and lots of carbon nanotubes and figure out all sorts of cool things you could do with them. And then in 2003, a couple of scientists by the name of David Warheit from DuPont and Chu-Wing Lam from NASA rained on everybody's research parade when they announced that actually carbon nanotubes show signs of toxicity if they get into the lungs. More specifically, if carbon nanotubes are spritzed into the lungs of mice and rats, those lungs going from being nice and healthy and pink, as you can see here on the left, to turning black from the nanotubes, to becoming inflamed. And when we look at them under a microscope, inside the lung, the cells go from being nice and healthy here on your left to forming these hard knots of tissue around the carbon nanotubes called granulomas that can interfere with the breathing and function of the lung. So this is really bad news, but it was not surprising news actually to a group of researchers like Ken Donaldson in Scotland who had been studying another tiny fiber for years called asbestos. And they pointed out that asbestos under the microscope structurally resembles carbon nanotubes. And because asbestos, as we know unfortunately from years of research, is very toxic and damaging to the lung and can even cause this rare type of cancer called mesothelioma, it's not surprising to researchers like Ken Donaldson that carbon nanotubes might have similar toxic abilities. So this news and the story at this point about carbon nanotubes is getting pretty bad. But there's a group of people for whom it is really, really bad. And that is not people out in the audience who are possibly enjoying bites that went into Tour de France or bulletproof suits. It's actually people who are manufacturing and working with and handling carbon nanotubes. Because if the nanotubes get accidentally into the air, they can then be breathed down into people's lungs where they can potentially cause damage. And I want to emphasize something here that nobody reasonably is going to go up and just grab a handful of carbon nanotubes and huff them into their lungs. There are two scenarios we can sort of expect where people would be exposed to carbon nanotubes, where nanotubes can get into the air. And one of those, as you can see here in this furnace in the center where carbon nanotubes are being made, would involve a failure of engineering controls. For example, if this furnace itself or these seals in the cabinet around the furnace or the ventilation that's pulling the nanotubes away, if any of those were to fail, we could start to get carbon nanotubes into the air where they can then be breathed in by the workers. And the second scenario that we're concerned about involves a failure of human controls, a failure of human behavior. For example, if somebody is not wearing protective equipment like a respirator or gloves, as you can see here on the left, or either through ignorance or what have you, is handling carbon nanotubes inappropriately. For example, as you can see here on the right from an American university, where researchers were actually just pouring carbon nanotubes from one bucket to another, letting them get up into the air like dust bunnies, where they can then be inhaled. Well, the story at this point is not looking good. We know that, based on what David Warheit and Chu-Wing Lam said, that carbon nanotubes might hurt your lungs. We know from what asbestos researchers are saying that they might resemble asbestos. And we know that people likely are already being exposed to carbon nanotubes. But at this point, researchers and regulators realize that we need to figure out what is the consistent story. Were David Warheit's and Chu-Wing Lam's results just anomalous, something that happened in the lab? Or were they part of a bigger picture about what nanotubes could do to your lungs? So researchers first in the United States came out with some early, more encouraging results. They said that when they exposed rodents, like rats and mice, to carbon nanotubes, they actually observed a lack of lung toxicity. So the lungs were not becoming damaged. So pretty good news. Which was then contradicted by additional results from Virginia, where researchers said actually when our mice inhaled carbon nanotubes, the nanotubes are triggering cell death, are causing parts of the lung to die off, directly contradicting what the other ones said. And then the story got even a little more confusing. when researchers in Scotland said, actually, our rodents aren't showing any sign of inflammatory response. There's no inflammation happening to their lungs when they breathe in nanotubes. While researchers in Montana were saying, actually, we see acute inflammation, this really rapid, really bad inflammation early on after the rodents breathe them in. And finally, as if it wasn't too confusing and contradictory, researchers in Germany said that, well, when our rodents breathe in carbon nanotubes, we're not seeing any sign of pulmonary fibrosis or this stiffening of the lungs that interferes with breathing. While researchers in West Virginia were claiming the direct opposite, that they saw rapid development of pulmonary fibrosis, this quick onset of the fibrosis. So what was going on here? Why was everybody getting all of these contradictory results and having all sorts of different ideas of what the story was about when carbon nanotubes get into lungs? Well, the key to this was earlier in my talk, when I mentioned that there are lots of different types of carbon nanotubes out there. There are long ones, there are short ones, there are thin ones, there are thick ones, there are ones that are covered in chemicals and bold and pristine. And when researchers were coming together to try to compare their results, it wasn't quite like comparing apples to oranges, but it was at least like comparing Golden Delicious apples to Honeycrisps, which are my personal favorite. And furthermore, researchers were not just comparing one Golden Delicious to one Honeycrisp, they were comparing one Golden Delicious to lots of Honeycrisps, a small amount of carbon nanotubes, or small dose, to a large dose, a large amount of carbon nanotubes. Furthermore, some researchers were giving the same dose all at once, kind of like eating an apple pie all in one sitting, which I do not recommend, versus other researchers who were giving the same amount, but over time. They were changing the frequency of the dosing, sort of like having a slice of that same pie every night of the week. The overall dose is the same, but the effect will be different. And finally, researchers were comparing the results in two types of rodents, rats and mice, which both mammals, both rodents, but both have different sensitivities, susceptibilities. For example, rats are a little more prone towards getting that fibrosis, that stiffening of the lungs I mentioned, and more prone to developing lung tumors. So if you were to expose them, the story might be a little different depending on who the characters are. Well, a number of researchers and regulators realized that we needed to come to some common ground if we want to figure out what could actually happen when carbon nanotubes get into your lung. We can't just keep going all over the place, grabbing random nanotubes, random frequencies of dosing, random doses, random animals, and then try to compare our results in the end. We have to come up with a systematic way to be able to compare our data and come up with a common story. So a number of labs in the US and a few overseas, one is my lab, are now working together in a collaboration where we've agreed to some basics. We're going to work with set species, a known dose of carbon nanotubes, known frequency of dosing, and most importantly, in my opinion, instead of just taking random carbon nanotubes, whatever we could get maybe from the manufacturer for free, we're going to be systematic about it. We're going to pull out a representative carbon nanotube from the ones that are on the market. A long one, a short one, a thin one, a fat one, ones that are hairy with chemicals, ones that are bald. So we can start to figure out which of these traits, which of these varieties of carbon nanotubes could be most responsible for the toxicity, for the damage they could do to the lungs. Because ultimately, we're not motivated just by trying to gain more esoteric academic knowledge. We're motivated by two key things. One is that when people are exposed to carbon nanotubes in the workplace, we want to be able to tell doctors who are treating them what they could expect might happen, so that doctors can maybe begin to mitigate those effects, to prevent them from worsening. And second, we want to be able to go to regulators and employers and employees and let them know what could possibly happen and what sort of controls, engineering and human, might be most important for keeping people from having their lungs get damaged. Because ultimately, as a toxicologist, that's what it all comes down to for us, is we want to know what are the bad things that could happen so that we can try to stop them, so that people can keep making and enjoying things safely. Awesome things like bulletproof suits, cancer drugs, and bikes made out of Sumio-Iijima's helical microtubules of graphitic carbon. And I just want to talk at the end, it's at the end, but I want to take a quick moment to thank a large number of people and organizations. First of all, I really want to thank the Engage program where I was a 2014 participant, and especially one of my teachers there, Juliana Houghton and Jessica Rode. And the Engage program was based out of the College of Environment at the University of Washington, where I am a PhD student in the toxicology program in the Department of Environmental and Occupational Health Sciences, where I have the privilege to work with my advisor, Dr. Terry Kavanaugh, and a number of excellent scientists, including Diane Botta, who's here in the audience too. And I also want to thank NIHS, which is the National Institute for Environmental Health Sciences, and under the National Institutes of Health for funding a lot of our research. And ultimately, I want to thank Town Hall Seattle for giving me and all of us this forum so I can talk with you about the perils and promises of carbon nanotubes. So, thank you for being my audience.
What university they were doing it with their hands from bucket to bucket with the nanotube? What university was that they were doing that?
That's a little. Oh, thank you. Without getting too specific, it was a university that is well known down in Texas.
And you're not at liberty to say for some reason, or?
It's a little awkward to point fingers because sort of encouraging them to change without accusing, but yes.
Yeah. Hi. Well, I guess I could have stayed in the audience, but I'm just following the town hall format. So thanks for your talk. That was lovely. I work in a lab that manufactures carbon, but not carbon nanotubes that I know of. They may have done this in the past. But I guess I wonder if if the exposure, the detrimental exposure that they're showing for the carbon nanotubes for the people manufacturing them was specific to that type of carbon as opposed to other carbon that might have been used in electronic devices or batteries.
Oh, so how specific is it?
Because the carbon I work with isn't carbon nanotubes, but it's used in similar electronic applications like that.
Mm-hmm.
And when you were to pour it from one bucket to another, it would go up in the air in that same way. So.
Well, I guess I would be a little worried about it.
Right.
Aerosolizing
so,
like that.
We wear respirators and things.
Good.
But I wonder if there's any
Yeah. I think that's a very interesting question about the type of carbon affecting the toxicity. I think with my particular research, it relates more to the actual shape that the carbon is taking, this fibrous shape. And what's interesting too about carbon nanotubes is, you remember at the very beginning when I showed that tangled knot of human hair looking under the microscope? Nanotubes rarely get into the environment in individual fibers. They usually kind of knot together like that dust bunny. So that's more of the effect is based on that size they take. It's about 1 micron, so 1/1000th of a meter. Yeah. And in that case, it would depend on often the size of what carbon you're working with would take. If it's pretty large, it would get caught basically in your snot if it was able to get through the respirator. Or if it was much, much smaller, it would still get caught, but there's a chance it could be working its way down deeper. But I'm really glad to hear that you're wearing respirators.
Are the people at that Texas university, are they aware? Are they still doing it that way? Or are they aware now that they're not supposed to do it that way? Or?
They should be aware now that they're not supposed to do that way. And I'm pretty confident they heard from a number of toxicologists when the picture came out. Yes.
What's the risk to the general public? Or
So-
more specifically me?
More specifically you. It's pretty minimal to the general public, mainly because you will mostly see carbon nanotubes in manufactured settings and research laboratories. So if you came and took a tour of my lab and started, I guess, opening everything up, you might get exposed. There has been some research showing that a few carbon nanotubes will be out in general, the general environment, mostly around areas with lots of traffic, because they can be created through diesel combustion. But they are, it looks like such a tiny fraction of what actually comes out of diesel combustion that I would not worry about that as a general population exposure. Okay.
So it sounds like the main problem or danger associated with carbon nanotubes is at the manufacturing stage. What about when your electronics are recycled or materials at the end of their life cycle are taken apart? Is there a danger also to the workers who are dealing with that end of the process?
Yeah, that's another really good question. I have seen much less research into exposure at the end of the life cycle, but it's definitely something that I would be personally concerned about. I think the exposure probably would be less because you are less likely to be working with the carbon nanotubes coming directly out of the furnace like I showed. But it's certainly something to keep in mind.
Are you able to tell us any results from your work, or are you still in the process of looking at all of these different carbon nanotubes, or any insights?
Any insights so far?
The answer?
Oh man, yeah, I wish I knew what the answer was. Things are still underway. It's the best way to put it. One of the sort of consensus that is emerging from the literature though, when I showed you that furnace earlier, so there could be several different types of nanotubes, and a lot of nanotubes when they're first manufactured, they're very dirty from the manufacturing process. They'll have a lot of sort of metals carried over, a lot of just extra carbon. And it turns out that often those dirty carbon nanotubes, before they've been cleaned up and further processed and be coated with chemicals, are probably the more toxic ones, which further underlines why it's so dangerous for people who are actually manufacturing and handling those early dirty ones. Questions? Great, well thank you again.